Hello and welcome to Module 3, Chapter 26. In this module, in this video lecture, I will be explaining Chapter 26. The chapter, we're not going to be covering all of it. Basically going to be covering two major topics. There are several topics in it, but two major topics. The first one is interference and coherent sources, which is section 1, and basically section 1 through section 2, section 1 and 2. Okay, it's all about interference, and then we're gonna jump to section section 8, which is circular aperture and resolving power. Okay, so we're just going to be covering section 1, 2, and 8. Those are the only sections that we're going to cover in this chapter. So I will try to cover both of them today, and hopefully I will do at least 2 problems for the homework and a couple of problems also from the examples and from my lecture notes. Okay, all right, so let's get into it. First, we talk about the interference of light. The interference is it is a phenomenon where how light, say 2 light waves interfere with each other. I'm not going to go into the details of that. There is some diagram, the one that you see in front of you right now, how 2 light waves interfere with each other, and as a result of that, you will see a bright spot right here at point P2, and sometimes you'll see at say point P3 here, there'll be a dark spot. Okay, and the reason for that is how the 2 waves meet here. You can have what is called a constructive interference and a destructive interference. Anyway, all of that is not terribly important for you to learn. What is important is the formulas that we're going to be dealing with. Let me go jump to them, and these are the 2 formulas, and there is one more I'll show you in a minute what that means. Okay, so the interference phenomenon, or what we call the Young's double-slit experiment, is an experiment that was done, I believe, in the late 19th century, and it was a very, very important experiment for determining how to measure the wavelength of light. Okay, that's really what's important. This is really what you need to learn, is how it's a way of allowing you to measure the speed of light, the wavelength of light. You remember when we covered magnetism and I showed you how it is possible to measure the mass of the electron, the mass of the proton, or any ion in the periodic table, whatever. And we said this is called mass spectroscopy, where you allow a particle to go through a magnetic field, and it will go around in a circle, and then you can measure the radius of the circle. I'm sure you remember all of that. So that was a way to measure the mass of a very tiny particle, such as at the atomic level or subatomic level. Well, this experiment, or this technique, is another way to measure the wavelength of light. And of course, light is in the order of the nanometer, which is 1/1000th of a meter. So this is an interesting experiment that allows you to do that. So let me just show you how that works. This is the 3rd equation, and these are when you look at the screen, it will look something like, let me give you a diagram. I'll show you how that works. So what Young has done is this. So he had a screen, and he had, in the screen, there are 2 slits, okay? A slit here, there are 2 holes here, okay? And the distance between those 2 holes is extremely small. I'm talking here something in the order of, say, 0.1 millimeter. Really, really tiny distance. The reason for that is because you want the length or the distance between the 2 holes compatible with the wavelength of light. Okay, so we call that slit 1, for example, and this is slit 2, S1, S2, this is what your book calls them. And then at the faraway distance, say 1 meter away, there is another screen here. And then by shining a beam of light, which is, say, the light that I'm interested in measuring its wavelength. Let's say, for example, I have the same setup. Let's say I'm shining a beam of green light. Okay, so this is the beam of green light, or any light that you want to. Okay, and of course I'm interested in the wavelength of it. Okay, the wavelength of this light. So what's going to happen is that the part of this light is going to penetrate through this slit, and the other part go through this slit. And then when you look at the screen in the dark, okay, what you'll see this picture, the one I just showed you. You'll see bright and dark fringes like that. You see that? That's what you would see. The dark fringes here, that means there is no interference. In other words, those two light beams going through the slit. So you get, let's say you have a dark, let's draw a line that goes, we call it the central axis right there. Okay, right at the axis here we will see a bright or central bright fringe. It's called central bright fringe. Okay, this one here, and then you're going to see another bright one here, another bright one here, and here, and so on. Of course, it's identical at the bottom as well. Okay, they're all symmetric, and in between there are dark. So this is dark right there, dark in between. So dark, bright, and so on. You get that? So so what happened is that this one beam of light, or one ray of light from slit one, let's say it goes right here. So let's assume this is bright, and then the other one comes from the slit 2 right here. Sorry. Okay. And as they meet, if the interference between them is constructive, you will get a bright spot. If it is destructive, let's say right the one below it right here, you will get a destructive interference. That is, you will get a dark fringe or dark spot. Okay, so the central one is always bright. Okay, and then this is bright. Okay, it's not dark, and then you get here they oscillate from dark to bright. Okay, now each bright one we numbered. So the first one here, the one that is here, is m equals 1. We call it, order. This is m equals 2, m equals 3, and so on. Okay, so that's the order. Which bright spot are we talking about? So the third bright, fourth bright, fifth bright, and so on. The dark thing is the same way. So first dark, second dark, and so on. Okay, so this is how we number them. And then if I assume that the distance between this slit here, this screen with the 2 slits, and the screen is a distance r. This is your book. I like the notation L, but your book uses capital R for that. And if we assume that the distance between the 2 slits, let me draw it again. Okay, and if we assume the distance between the 2 slits is small letter d, again I'm using your book notation, and let's say, for example, we're talking about some spot here, whether it's dark or bright. Here it is, both rays coming to the same point, joining here, interfering. Okay, this angle, or this angle right here with respect to the horizontal, is angle theta. Okay, and then you have, again, we said that the distance here is r between the 2 screens. And let's say I am studying this spot right here, whether it's dark or bright, it doesn't matter. Okay, some m value, m equals 1, 2, 3, 4, whatever. Okay, the distance between them, the distance or the height to this spot from the central axis, we call it y sub m. Okay, y sub m. So for example, if m here is 3, so it becomes y sub 3. You got it? Okay. So what are the relationship between all these variables? Well, there are 2 or 4 important formulas. The first one is this one, and let me show it to you in the book. This was the last one. Right there. Okay, so for constructive interference, it says d sine theta equals m lambda. This is for bright. Okay, when you say constructive, see the word constructive right there? That's bright. Okay, now for destructive interference, we call it dark, and you have the same formula except m here, and then you have m plus 1/2. You got it? Okay. So let me write down those two formulas. So for bright, so it is m lambda equals to d sine theta. Okay, that's the first formula. And remember, theta here is, oops, theta is right here, this angle right here, okay? And m is the order number, okay? Now for dark, it's the same formula except that you add a half because it's half a wavelength equals d sine theta. Same thing, d sine theta. But for dark, you always add that 1/2. So if you see a half here, it means it's a dark fringe. Now the other one is that if I am interested in finding the height to whatever order, whatever, to dark or to bright, okay? So the height here, again, you can look at the derivation, but I'm not going to derive it here. You don't need it anyway. So y sub m for bright, this is for bright. Y sub m is equal to, go back to the book, let me show it to you. Next page. And it's right there, okay? Y sub m, r m lambda over d, okay? So it becomes r m lambda over d. Again, d is the, it's the distance between the two slits. You got that? Okay. For dark, the same formula, except that you replace the m with m plus half. So it's going to be y sub m is r m plus 1/2 lambda over d. Got it? Okay. What else? Okay, so that's basically the subject of interference, okay? Let me show you an example. I'm going to do at least 2 problems, so just to get you, and they're not going to get any harder than that, whether in the quiz or the test, whatever. So let me start with example number 26.1. There is a little trick to it, this example. That's why I want to do it. Let me look into it. Let me look at it in the book, that is. Here it is right here. It says, I don't know if I can magnify it with my hand a little bit. Whoops. I messed it up. Sorry. There we go. Oh, I can't do it. Let me do it. Try it again. Oh, here I can magnify it. Here, this place, I think. There we go. Okay. It says, let's begin by using the 2-slit. Okay, we start with here. So we have here. So you get this. Here is the setup right there, the experimental setup. So here the light coming, ignore this this screen. Basically you have a light coming. Here are the 2 slits, right? The distance between them is 0.2 millimeter. Look how small it is, right? You could barely see them with your eye if you're in an actual, if you're actually looking at it. And then you have the light coming through them, and then the light shine on the screen here. Then you will see bright and dark fringes like that, okay? And in the central, I'm sorry, okay, our book uses the central to be m equals 0. Notice that? This one m equals 1. Some books use it differently. So let me go back to here. So the central one here is 0, okay? I just want to make sure. Some books, they use this m equals 1. It depends on how you set it up. But anyway, okay. So here we have, this is what we got, the screen, and we got the dark and bright fringes like this. The distance between the 2 screens is 1 meter. So let's read it now. It said, with the slits 0.2 millimeter apart, right here, and a screen at a distance of 1 meter, the third, listen to this, the third bright band, which is 1, 2, 3, right here, okay, starting from 1 here. So m equals 1, 2, and 3, right there. The third bright band out from the central bright band is found to be 9.49 millimeter from the center of the screen. In other words, the distance, here we go, the distance from the central axis right here to the third bright is this number, 9.49 millimeter. Okay. The question is, what is the wavelength? There we go. This is basically why you need this experiment, why you need to learn about it, is how to measure wavelength, the wavelength of light. So what is the wavelength of the light? Okay, so let's do that. Well, how do we do it? let's go over it. So what I have in here, here is the double slit. Here is the screen. Here is the central line here, the central axis, whatever you want to call it. And then we are getting, so the light is coming this way. Here's the light green or whatever it is, some lambda. We want to know that. And then here is the m equals 3 right here, right? And he said the distance here, y sub 3, is 9.49 millimeter. Watch those units, okay? And he wants to know lambda, okay? Now, since it is bright, you need to know whether it's bright or dark because it has a different formula. So this is bright because he said the third bright band, right? So what we do now, we go back to the formula. Let me look it up in my notes rather than. Here it is. So we have y sub m is equal to r m lambda over d, correct? And I think we have everything. This r is 1 meter. The distance between them here is given to us. I forgot what the number is. What is it? 0.2 millimeter. So this is 0.2 millimeter. D is 0.2 millimeter. And I think we're ready. So all you need is just to solve for lambda. So lambda in this case is going to be equal to, what is that equal to? Y sub 3 D over mr, correct? Is that right? So we plug it in. So we have, everything is given to us. So y sub 3 is 9.49 times 10 to the negative 3 times d, which is 0.2 times 10 to the negative 3, divided by m is 3, okay, times r is 1 meter, okay? And then we calculate that. And when I do the calculation, there we go, I think he did it the same way. And there we go, he got the lambda, he plugged in all those numbers, and then he got it to be 633 times 10 to the negative 9. So basically it is 633 nanometer. There we go. We got the nanometer. You can, of course, you can look up a table and say which color has a wavelength of 633. I'm not sure what it is. I know 550 is green, so this one is a larger one. So it's after that. I don't know if he says anything about it. Probably blue because he has a blue color here. Maybe. I'm not sure. But it kind of sounds like blue. Anyway, there we go. This is how you do that, okay? That's part A. Now, the reason I want to do this problem is also because of part B. It can be very confusing, and it's only unique for this textbook. Now, let's read it first, and I'll show you why it's confusing. He said, B, how far apart would the slits have to be? He basically asking for a D here, okay? How far apart would the slits have to be so that the fourth minimum, the word minimum, by the way, is also mean dark. So maximum means bright, minimum means dark, okay? So now we have 3 words for dark and 3 words for bright. For bright, you have the word bright, constructive, and maximum. For dark, dark, destructive, minimum. You got that? Just the language, just the lingo. Okay. So he said, how far apart would the slits have to be so that the fourth minimum, which is dark, would occur at the same height, 9.49, from the center? In other words, what would D be? But here is the thing. When he says fourth dark, he doesn't really mean fourth dark. He really means always subtract a 1 from it, okay? I don't know why the book does that, but there is a homework problem, the same thing. So if you see the word dark, he says fifth, make it 4. If he says third, make it 2. You know what I mean? So fourth dark, it means m equals 3, okay? Fourth dark. Got it? This is important. It's kind of confusing. When I actually did this example, I thought m equals 4, and it turned out that it's not the case, so he put that m equal 3. He gives you an explanation here why he did it, but just remember that, okay? Other books, when they say fourth dark, it just means 4, okay? Anyway, so he wants to know the D here. So let's do it. So we know that we gotta use the formula that's similar to this one for the dark, which is this one. Y sub m is R m plus half lambda over D, and of course I'm solving for D, right? So therefore D in this case would be equal to R m plus half lambda over Y sub 3. Remember, fourth dark means m equals 3. Just subtract a 1. Got it? Okay. Plug it in. Simple. So therefore, D equals to R, which is 1, 3 plus half. Okay? Lambda, I just got it. He said with this wavelength right here. So 633 times 10 to the negative 9 divided by Y sub third. He said it's the same number. 9.49 times 10 to the negative 3 makes it in meters. And then you calculate that, right? So when you calculate it, I'm just going to get the answer. There we go. We did exactly the same thing. And it turned out to be 0.233 millimeter. Okay, so 0.233 millimeter to get that fourth dark or a third dark. Okay, got it? Okay. Let me do one more problem from the homework. Let me go back to my book. I'm using the hardcover because I can get there quicker. Then I'll show you where is it in our ebook. I want to do number number 6. Yeah, I want to do number 6. Okay, I believe it's a homework problem. Let me go to the book. Here it is. How do I go back to normal? That's normal, I hope. Oops, disappeared. Ah, not good. There we go. Okay, hopefully this is normal. All right, let me go to... We are in 26. We're going to do the problem, summary. Should be after summary, right? Okay. Number 6. There we go, right there. Okay. Maybe I can magnify it again. There we go. So it says right here, see that? It says a coherent light. When you say coherent, it means the same color. It's not mixed colors and so on. So I have a coherent light of wavelength 525 nanometer, passes through 2 thin slits that are 0.0415 millimeter apart, then falls on a screen 75 centimeter away. Okay, so far nothing new. We've seen all that. He said, how far away from the central bright fringe, which means from the center, right, on the screen? That is the 5th bright fringe, not counting the central, which basically for bright, it just m equals 5, basically, okay? And then the second part, look at the sneaky part. He said the 8th dark fringe. So what does that mean? 8th dark, it's m equals 7. Got it? Okay. Let's do this problem very quickly. I think I have it solved here. Just cut the time in terms of I don't think I have it, do I? I don't. I'm sorry, I'm taking too long. There it is, right here. Okay, let's do it. Okay, so number 6. This is number 6. So let's write what's given to us. He says coherent light. So the wavelength is 525, and the distance d, the small d, the slit width, or excuse me, the distance between the 2 slits is this number right here, and it is away 75 centimeters away, and so on. So what I have the following data. So lambda is equal to 525 nanometer, and I have D to be equal to 0.0415 millimeter, and I have R is 75 centimeter, okay? And then part A, he said he wants M equals 5 for bright, okay? Basically, he wants Y sub 5, okay? And of course, as you know, Y sub M is right here. Let's scroll down. It is similar to that right here. Whoop. Similar to this one. This one, except that no how this is for dark, right? So it's going to be R M lambda over D, correct? So we have R is 0.75 meters, right? Remember, this is 0.75 meters. This one, 0.0415 times 10 to the negative 3 meters. And then this one, of course, 525 times 10 to the negative 9 meter, okay? So we plug them in. So we have here 5, and then lambda is 525 times 10 to the negative 9 divided by, and then we have the distance between the two slits is this number right here, 0.0415 negative 3, and then you plug in all this data, and when you plug it in, I'm looking at my notes here, I got 0.0474 meter. Okay, there we go. Simple. Okay. Part B, he said the ace dark. Let's read it again. He says, how far away from the central bright fringe on the screen, part B, the eighth dark fringe. The eighth dark fringe. So eighth dark means M equals 7. Get that? So we can do it. So Y sub M equal to M plus 1/2 R lambda over D. Is that right? Just plug it in. So we have 7 plus half. R is 0.75 times lambda 525 negative 9. All of that divided by 0.0415 times 10 to the negative 3. Plug all that stuff in, and I got, looking at my answer, I don't know what I got. I believe I got, please do my calculation, 0.0716 meter, I think. All right. And there we go. Got it? Simple? Okay. Okay, now let me move on to the next topic, which is the last topic we're going to be covering in this chapter. And by the way, this is the last chapter in the subject of optics. And then starting next week, we're gonna be working with 20th century physics. So we're going to begin with the study of relativity. I think it's going to go for 2 weeks. I'm not sure. And then nuclear physics. So basically, really, we have 2 more chapters left. But they will take us, I believe, both of them, each of them, going to be for 2 weeks. Let me check very quickly before I forget to mention that. I go back to the course schedule here. We are right now, yeah, that's true. So right now we are here, module 3, interference and diffraction. Everything is due on the 12th, which is this Sunday. And then for the next 2 weeks, we're going to be studying relativity theory. And then that we'll be done with it around the end of the month, April 26th. And then after that, we're going to take up nuclear physics for 2 weeks, and that will be the end of it. Okay, so we have basically 4 more weeks to go, and then after that, the final exam. Okay, don't take this date seriously. I should have written to be decided, whatever. I mean, I don't know. I haven't really looked up the schedule, so this is subject to change. Anyway, okay. Back to our study. The next topic that I want to talk about is the resolving power of an optical instrument. What am I? I believe it's section 8. There we go. This is an interesting topic, and I find it important for those who use optical instruments, such as you guys who are into the medical field. I can imagine you use a lot of microscopes and other stuff. So this stuff is important. And for us in astronomy, for example, it's an optical instrument that we use, that what is called the resolving power of an optical instrument. You see what I'm saying? So what is a resolving power? A resolving power is the ability, I mean, for example, when I say what is a resolving power of an optical instrument, it means it is the ability of this optical instrument to distinguish between two closely spaced objects. Okay? Let me explain. I am sure you've probably been on the highway traveling to some distant place on the middle of the night, for example. Okay? Let's say you're driving down the highway, it's 2 o'clock in the morning, and there's no cars at all, for example. It's really dark. I've been in that situation many times. That's why I'm bringing this example. And then at very far away distance, you see a car coming. Okay? I mean, you're going northbound and the car is coming, southbound, the other side of the highway. You see a car coming, and all you see really is one spot of light. Okay? And at far away, you may assume it's a small car. Okay? And as it gets closer, well, it turned out that it's not really one spot of light, but it's actually two. Basically, the two headlights of the car. Okay? You say, okay, it's a two headlight, but because it was so far away, you couldn't distinguish between the two headlights. You only saw one headlight. You see what I'm saying? And then as it gets closer and closer, oh my gosh, it's not even a small car. That's a big, giant 19-wheeler, 18-wheeler. It's a big semi-truck. Just comes past by you. Okay? So you didn't see any of that from far away, right? All you saw was a small spot of light. You assumed it's probably a motorcycle or a small little car. But because it was small... Now, as it gets just far enough, at a certain point, your eye is capable of seeing actually two headlights. This is called the resolving power. So let me repeat the definition of a resolving power. A resolving power of an optical instrument, for this case your own eyes, your own pupils, okay, is the ability to distinguish between two closely spaced objects. Of course, here we're talking about the spaced object are the two headlights of that big semi-truck. At far away, you only saw one spot of light. As it gets closer, now you see two spots of light. You see what I'm saying? As it gets even closer, those spots of light are actually too far away. They're probably 5 yards away. This thing is very, very wide. You see what I'm saying? So that's basically what the resolving power is, that how close you have to be able to distinguish two things that are closely spaced, such as the headlight. Okay? Another example, I remember, for example, I remember hiking on a trail in a place where there's a lot of trees in there. And I remember seeing a tree at far away distance, a big tree. I think it's an oak tree or something. And all I saw was green. The tree was green. As I got closer, I saw two black birds standing on it, standing on the tree. I see them. I see two black birds. They're far away from each other, but I can see two of them. But as I have gotten closer and closer, and I'm talking really close, I looked at the tree and there were like 50 birds. They're all identical black birds. They were just standing there. However, I did not see them when I was far enough. All I saw is a green tree. Okay? As I got closer, I'm able to see not just a bird. I'm actually seeing the leaves. See, when you look at the tree from far away, you're not seeing the leaves. All you see is kind of a smudge, just kind of a green spot there, but you're not seeing any details of it. But as you get closer, you start seeing leaves, you see branches, maybe you see a bird nest, you see a bird or whatever. You see in other words, you see details. And the reason is because it all depends on the resolving power of your own eye. The same thing is happening, for example, another example is when I look through a telescope. I don't have a telescope, a binocular, okay? I mean, astronomical binocular. I have it at home. It's not terribly strong or anything. But when I look at our closest star, which is Alpha Centauri, I see one spot. just one spot. However, if you look at through that star, look at the star through a larger telescope, say an 8-inch or 14-inch telescope, it turns out that it's a binary system. In other words, there are two stars, Alpha Centauri and Beta Centauri, that are going around each other. You'll actually see two. But your naked eye, or the binocular that I have, you only see one spot. Okay? Why? Because my eye is not strong enough to resolve those two objects that are closely spaced with each other. Got it? That's basically the subject, what the subject is all about. So let me just show you some mathematics here. And then we'll do at least a couple of problems. The subject is interesting and it's not terribly difficult. You just need to know the notation. And this is the formula that we will be using. Actually, that's not we're going to forget about the sign thing. There's another version for it. This one is fine, but there is another version for it. And that is, should be here. It's called Rayleigh's Criterion. This is the one right there. This is the formula that you need to do. So maybe when I write it down, but that's the formula that you need to know. Okay, it's called Rayleigh's Criterion. Theta, I like to call it, what RES stands for? Oh, resolution. Okay, I like to call it theta min, minimum. I'll tell you why I call it that. Theta min equal 1.22 lambda over d. Okay, and then it's almost equal to. That's not equal to. So anyway, my version of it is this. So we'll say it's Rayleigh's Criterion formula. It's basically theta min is almost equal to 1.22 lambda over d. Okay, that's what it is. Now, what is lambda? Okay, you know what lambda is. It's basically the wavelength of the light that I'm dealing with. Okay. For example, I'm looking at, let's say I'm on the highway. Go back to that highway example. I'm looking at that one spot, a car with one spot of light. Well, that light coming from the car is the wavelength that I'm dealing with. Okay, or if I'm looking at Alpha Centauri, the star, and the light that is coming from Alpha Centauri is the wavelength of that light. You got it? Okay. 1.2, don't worry about it. It just comes with it's heavy mathematics. Why this number? Just accept it. Then d here is the diameter of the objective lens. For example, here's my eye, right? Right, there's the diameter of my pupil is d. Okay. For a telescope, or let's say I have a telescope. Here's a telescope, and so the diameter of the lens here, okay, whatever it is, that diameter is d. Okay, it's called. There is a name to it. It's called the aperture, or the width of the aperture. Aperture width. Whoops. Aperture width. D. Okay, aperture width, or the width of the aperture. Okay, basically the diameter of the objective lens, or for the case of my eye, the diameter of my pupil. Got it? Okay. And lambda, of course, is the wavelength of light. Okay. Now, what is theta min? What does that mean? I'll tell you. Let's say, for example, I am looking. Here is my eye. Okay. And I am looking at a distance, say, remember this. Let's say this distance, let's say a mile away, really far. Okay, and I'm looking at a bird. Here's a birdie. Okay, assume it's a small bird. I can draw a bird. There it is. Now remember, I am about a mile away. Far. Now, when I look at it, I may not see it because it's so small, it's so far away, the bird is small, I can't see it. But, so here is the width of the bird, or the extension of the bird from here to here. Let me put it from here to here, sorry about that. Okay, let's say the bird is this way. Here's the bird, okay? So my eye, in order for me to see the bird, I have to see the extension of the bird, from the far left to the far right of the bird. So here is the eye. That is the light coming from the bird, like this, right? So this is the angle of the subtended theta, and that's the width of the bird or the height of the bird, whatever it is, okay? This is the distance to the bird, okay? The smallest angle, okay? The smallest angle that the width of the bird subtends at the aperture is still resolved, okay? So in other words, what's the smallest angle I can have in order for me to see the bird? I mean, wider than that, I can see it. See, if my eye is here, look at that. Here's my eye. Look at the angle. It's much wider than that. If my eye is way down here, you know, when you extend it like that, the angle is really small. So maybe you will not see it. But as you get closer and closer, as you become closer and closer to the bird, this angle gets bigger and bigger. Well, what is the minimum angle that I am able to see the bird? And that minimum angle is given by this formula. 1.22 lambda, which is the wavelength coming from the bird, divided by the width of my objective lens, the width of my pupil. Okay? Let me give you an example. I hope you understand that. Oh, one more thing. So if we call the width of the bird S, this is what your book calls it, okay? Or not just a bird, anything, any object that I'm talking about. So the width here is S. And then the distance from my pupil to the bird is, you know, what we call far away. Let's call it R. Is that what it's called in the book? Hold on, sorry. I think it calls it R. S. Oh, okay. Your book uses weird stuff here. Okay, he calls this S. I'm just going to stick with the book. He calls this S, and he calls the height or the width of the bird Y. I'm copying it from example. Yeah, let's do this example maybe. Example, okay? So basically, let me show you. You remember when you studied in geometry? If I have a circle and I have an arc here, and this is the angle theta, and this is the radius, let me call it R, how those three are related to each other. If you remember, S equals R theta. Remember that? The arc length is equal to. So look at that. Look at this. Look at this and compare it here. So here is the bird. All right, the bird right here. And here is where my eye is, right here. So you can see that this angle, theta, which is right here, so you can think of this as the S, and this is R. See that? Theta equals S. And that's basically what it is. But your book uses this weird symbol. So he calls this S, and he calls this Y. Sorry about that. But that's how he does it, okay? So the width to the bird is S, and then the how far is it to the bird or whatever. And then the angle here, this is the Rayleigh's Criterion. You got it? Okay? All right. Let's do an example. I'm going to do two of them. So where is that? Which one? Oh, yes, I have it in my notes. This is not in the book. Let me find it quickly. There it is. Okay, I'll do one from homework as well. So I have two more problems to do. Okay, says the example. Human eye versus eagle's eye. Okay, that's the title of it. Okay, so it says, imagine you have a hand glider. Okay, so let's say that you are on a hand glider. How do I draw a hand glider? Something like this. I don't know. Let me just give it like that. Let's say you are here. Here's your face right here. Here's your eyes. And let's say that, there we go. I don't know. Here's your arm. Here's the legs. There we go. Anyway, so let's say here's the ground right here. Okay, whoops. Here's the ground. And you are at the height of 120 meters from the ground. Okay? and that is, you know, you're looking at. Sorry, let me just read a green light. I enter the people. Okay, so let's say you are, you know, there is grass here. Okay, this is grass. So you have green light coming in. So we have green light. We're dealing with green light, which means lambda in this case is 550, I think, isn't it? 555 nanometer. Okay. So here's a hand glider, your high test green light. The green light enters the eye through the pupil. Once you mention pupil, that means we have the objective lens, or the aperture width, and it's equal to, for the human eye, is roughly 2.5 millimeter. Okay, that's the width of the human pupil on average. The question is, how far apart 2-point object must be on the ground if the pilot, if you, that is, this is the pilot right here, if the pilot is to distinguish, if the pilot to have any hope of distinguishing between them, is to distinguish between them. In other words, let's say I'm looking at a mouse. Okay, so there's a mouse right here. Okay, let's make the mouse just a little block. Okay, so that's one end of the mouse, and this is another end of the mouse. Now, if I don't see both ends, I'm not going to see the mouse. I'm just going to see green grass. You see what I'm saying? So he said, how far apart must they be? He said, how far apart the 2-point object? In other words, he's looking for the width. What would be the width of the mouse? The minimum width of the mouse in order for me to see it with my pupil if I am 120 meters away. You got that? So the way you do it, well, first of all, you draw, you know, very similar to this graph right here. Okay? So you draw the lines. Again, I'm going to try my best to draw a line that goes to one end of the mouse. Again, we call it a mouse. To the other end right there. And this is theta min. If I find theta min, I find that width. Okay? And we're going to call this width. We are calling it, what did we call it? I'm just going to stick with the book. He calls it y. Okay. So we're going to call that y. And then this one is S. This is really, I'm sorry, this is S right here. Sorry. Right? So it is this as well, right? Okay. And he wants how far. This is really what he's looking for, this y. We don't know theta min. Okay? Well, we know that theta min is equal to what? 1.22 lambda over d. I have everything. But remember, also, theta min is equal to what? From geometry, there we go. Go back to that formula right here. See that? So here, theta is equal to S over R. For our case, it's not S over R. We call that Y, and we call that S. Sorry about that. That's what your book uses. So theta as well is equal to, what is it? Y over, sorry. Well, it's right here. So theta for this is theta equals ys. So is y equal, I'm sorry, hold on. So y is equal to, just use that formula, it is s theta min. So therefore, theta min is equal to y over s. Is that okay? There we go. Here's another formula to add. So those two are equal, okay? In any problem, really. So make sure that you keep those formulas handy. So I'm going to equate them together. So I have 1.22 lambda over d is equal to y over s. Remember, he's looking for y, right? The width of the mouse. So y in this case is going to be equal to 1.22 lambda s over d. Plug it in. 1.22 lambda 555 times 10 to the negative 9 times s is 120 meters, right? All of that divided by, hold on, let me cancel this. There we go. Divided by d, which is the aperture width, or the width of the human eye, the human pupil, and that's equal to 2.5 times 10 to the negative 3. It's right there, okay? And then I plug in all that, and then I plug it into my calculator, and when I do it, I end up with 0.033 meters, or 3.3 centimeter, okay? That's for human. In other words, the mouse have to be at a minimum, a width or a length of 3.3 centimeters, which is about, what, an inch and a half, in order for me to be able to see it, okay? Now, let's apply this exact problem, except now we're going to replace the guy on the glider with an eagle, okay? So now we have an eagle eye. Here is the eagle eye, okay? So what would be the minimum width? You would think it's going to be smaller, right? Because the eagle eye is stronger. So how about an eagle eye? Well, the difference between the eagle eye and the human eye is that the eagle eye's pupil, D for our eagle, is equal to, I'm looking it up here, is wider, 6.2 millimeter, okay? So it has a huge, I mean, it's almost 3 times. Ours is only 2.5. You see what I'm saying? Ours is 2.5. The eagle is this. So basically what I'm going to do, I'm going to use exactly the same formula for the eagle. So Y is going to be 1.22 lambda S over D. All the numbers are the same except the D. You're going to plug in this one. You do it yourself, and you'll end up getting 1.3 centimeters. So the human eye will see it at the minimum have to be 3.3. For the eagle, only 1.3 centimeter will be able to see that mouse or whatever it is. Okay. One more problem, and it's from the homework, I believe, number 44. 44. There's a lot of talking in 44. Let me show it to you here. Chapter 26. And that's the probably the last problem I'm going to do today, and a little slow. .44. It's right here. Let me make it bigger. There we go. Okay, this is the one right here. I think you can see it with the mouse right here. Okay. Okay, let's read it together. The reason I'm using, I chose this one is because he uses some kind of different units that some of you have never seen, so I wanted to help you with that. All right, he says due to blaring, is that 44? Hold on, I want to make sure I want to do 44. Yeah, that's the one. It says resolution of telescope due to blaring caused by atmospheric distortion. The best resolution that can be obtained by a normal Earth-based visible light telescope is about 0.3 arc seconds. Okay, this is the minimum angle. This is a measure of an angle. I'll talk to you about it in a sec, but just that's what it is. So we have an angle of 0.3 arc second. Okay. A. Using Rayleigh's criterion, calculate the diameter of the Earth-based telescope. He basically wants the D, you know, the aperture width. Telescope that gives the resolution of resolution with 550 nanometer light. That's about green. Okay, that's the first part. Okay, let's look at it. Let's put it right there. I have an idea. The edge of the video, you should be able to see it up to here. Okay. So number 44. So what's given to us here is that theta min is 0.3 arc sec. What's arc second? Well, okay, you know, if you have 1 degree, okay, if I have an angle of 1 degree, and then I divide it into 60 sub-angles, you see what I'm saying? It has 60 arc minutes. Okay? Now, when this arc minute is equal to each one of 1 arc minute, 1 prime, okay? An arc second, if I take this 1 arc minute and divide it into 60 further, okay? It becomes, you know, 60 arc second becomes arc second. Got it? So the double prime is a arc second, 1 prime arc minute, and the little circle is a degree. Got it? But here is basically what you need to know. You can look it up on the web or whatever if you want to learn more about it. But basically, 1 arc second is equal to 1 over 3,600 degrees. Okay? Anyway, honestly, this is not important. You're not going to see it on the exam. So I'm just saying. Okay, so don't panic. Okay, another relation that is interesting. I need to look it up for. There it is, right here. This is what you need to know. 1 arc second is equal to 4.848 times 10 to the negative 6 radian. Okay. Remember, the going back, I forgot to mention that theta criterion. This one, the minimum, Rayleigh criterion, 1.22 lambda over d. I forgot to mention this must be in radian. So if you see a problem and he gives you theta criterion as 1 degree or 3 degree, whatever, you must convert it into radian. You got that? So this must be in radian. I forgot to mention that. Well, I forgot to mention because we haven't seen any problem like that. So you need to mention, you need to convert to radian, but that's how you convert, okay? So that's 1 arc second is equal to that. This is not important, really. This is what's important right here. Okay, so this is what's given to us. And then also he said, what? Due to this, using Rayleigh Criterion, calculate the diameter of, so he wants to know the diameter, which is basically big D. Here's the formula. This is given to us. This is, he wants that, and this is given to us. So that would be easy, right? So theta min, let me just write it down again, is 1.22 lambda over d. So therefore, d is equal to 1.22 lambda over theta min. But before I do that, I need to convert. Oh, so we know that 1 arc second is that. So 0.3 arc second, it will be what? You're going to multiply that by this number, right? That's going to be, to turn it into radian. So theta min, I'm sorry, let me do it better. Theta min is equal to 0.3 times 4.848 times 10 to the negative 6. And when I multiply that, let me multiply it quickly. So I have 0.3 times 4.848 to the power of negative 6. Let me do my calculator. And that will be equal to a 1.45 times 10 to the negative 6 radian. That's what I'm looking for. Got it? Okay. That's the hardest part about the problem, just the conversion that. So anyway, we got it. So therefore, D is just 1.22. Lambda is, what is it? I forgot. 550. I have the hard copy beside me. Divided by theta min, which is 1.45 times 10 to the negative 6. We plug in all of that stuff, and you'll end up with that the diameter of the objective lens is going to be 0.463 meters, which is pretty big, 46.3 centimeters. It's almost half a meter, half a yard. The width of the aperture width. Okay, all right, fine. And And then part B, he said, increasing the telescope diameter beyond the value found in part A will increase the light gathering. In what ways the kick the... Okay, this is just a conceptual question. I'll leave it for you. And that's it. Got it? Okay, I think I'm going to stop here. That's all you need to learn for this chapter. Please, I have, as you know, I have created the discussion forum. You know, you are more than welcome. Just tell me, hey, Dr. Raja, can you help me with problem number 55 or something? And, you know, chapter, whatever. I'll be more than happy to help you with that. Just, you know, post it there. I'll look it up and I'll solve it for you. I will either type it up or maybe I'll just solve it on a piece of paper. Then I'll take a picture of it and just post it there. Okay? So you're welcome to do that. You know, you can ask me. I will check it every day. Okay? One thing, another thing I want to mention. I get some emails from students who have, you know, let's say they entered the wrong number in their while taking mastering physics quiz or homework. And then they say, hey, Dr. Wright, can you please help me with that? I entered it. I meant to put 7.2. I put 7.1. You know, I don't want to be rude or anything. I'm sorry. I'm not responsible for those typographical errors. This is your ratio. Okay? I cannot deal. So if you put something wrong, you put the wrong unit, you know, don't come back to me on this. I'm not going to help you with it. I'm sorry. Okay? I will help you only if there is something wrong with the question, the wording, or something wrong, definitely wrong with there is an error in the mastering a problem or whatever. You know, then I will look into it. But if you've made the mistake yourself, that's just your responsibility. Okay. Okay. That's it. Have a great week, and look forward to listening to your, you know, reading your question if you have any.